In any system, energy is also conserved. So this type of motion is no different. And when I say energy is conserved, I mean that the potential energy plus the kinetic energy is going to add up to some energy total or a constant value. And we know from the previous video that the potential energy is 1/2 kx squared, and that kinetic energy from a few chapters ago is 1/2 mv squared, so that would be equal to that constant value. For a pendulum, however, we would need to substitute a few of the terms. So instead of 1/2 kx squared plus 1/2 mv squared for a pendulum, and this is only for something that exhibits circular motion, we're going to have 1/2 ml squared omega squared plus 1/2 mgl theta squared. And that would be equal to our total energy or a constant value. So I know I've already talked about this image, but we're going to look at it a little bit differently. So out here, when it is not moving, it's got this potential energy. And as it begins moving back in the negative direction, it has a negative velocity. It's going to have kinetic energy and then go back to having potential when it briefly stops and heads back in the positive x direction or has a positive velocity. And this is just going to continue back and forth. Now we can manipulate these equations and actually find that the max velocity is going to be equal to x multiplied by k divided by m. Or for anything exhibiting circular motion, it would be omega max equals theta max, and that would be g over L instead of k over m. But it is the same concept. Okay, here we have a merry-go-round, and this merry-go-round exhibits circular motion, which we are about to talk about how that is just another form of simple harmonic motion. We can actually prove this, and I will show y'all a better image in a couple of slides, because we can show that this circular motion shows a wave pattern if we run a piece of paper under it, and I will show y'all that in a moment. If a point is moving in a circular path and it has a constant velocity, then we say it's experiencing uniform circular motion, and the position there would actually be equal to x cosine omega t. Don't worry, we're not going to do a lot with circular motion. I just wanted to point that out. Now, this is the same image from a few slides ago, and now we see the paper under it and how the light spinning in a circle actually shows a wave-like pattern if we put a piece of paper under it. So this is what it looks like, and if we actually graphed that to show the 0, positive x, and negative x values, this is what it would look like. Now, in order to counteract this oscillating motion, we have what are called dampening forces, and they literally dampen the amplitude of the force. So some of them are natural, like friction or air resistance, but we are constantly having to counteract these dampening forces to keep a system oscillating. So that's why we see this example of a child being pushed on a swing. That mom would need to constantly push the child, otherwise dampening forces would take over and the child would eventually stop swinging. A little more about damping. So we refer to this as damping, and this is a graphical representation of a small amount of damping. Notice here that the only thing really changing is the amplitude. So the amplitude is slowly decreasing, but the period and frequency, they're nearly the same. They are not really affected. So damping affects the amplitude of the wave. This is another way to look at damping, and here in curve A, we have what we call critical damping, and for curve B, we have over damping. So we could have no damping, under damping, over damping, or critical damping. So in critical damping, I've said that word so many times, okay. Critical damping, you're going to see the system return to equilibrium as quickly as possible. And there are plenty of times when we would want this, like in a car's shock absorbers. You would want the car to stop oscillating very quickly. Not the car, but the springs in the suspension system. And then we also have overdamping, which I mentioned here. So overdamping and critical damping. So again, critical damping, we want to, it returns to equilibrium in the least amount of time possible. And that stands for amount of time. And you see that here it takes a shorter amount of time as compared to the overdamping. And there's very little back and forth movement here with the critical damping, whereas overdamping, it's going to overshoot that equilibrium position a few times, but it will return back fairly quickly. Okay, we see this image here again. Actually, I don't even think I meant to put this in here. I've already explained it, so just keep going. All right, here we have piano strings, and we know that in order to make them oscillate, you would have to strike a key, and the little knocker inside would hit the string for the piano, and it would produce an oscillation, and we would hear a sound from that. Well, we can force oscillations like that, but all objects are going to vibrate best at what we call their natural frequencies. Okay, so this is the frequency at which objects oscillate best. And when we are able to achieve this, we refer to the achievement of the natural frequency as an object's resonant frequency. Okay, so if you hear resonant frequency or resonance, it's just referring to the natural frequency of a system or the frequency at which the object will oscillate best. Consider this example. If you've ever had one of those toys, or you've done this on a trampoline maybe, you have a string attached to your finger and there's a little ball on the end. At some point when you're moving that, you can achieve a really large bounce from the ball, and it feels almost effortless. At that point where it feels effortless, you have hit the natural frequency. You found the natural frequency of this system, and so it is now resonating at that natural frequency. If we go too far past it, the ball will barely move. So if you just start shaking your finger up and down too hard, the ball won't really go anywhere. And if we don't do it enough, again, the ball won't go anywhere. But when we hit that perfect point, the resonant frequency, the ball will go very high, so we'll have a really large amplitude, and it will feel almost effortless to us. And that's just something to help you connect what's going on here. Here's another way to look at damping on a graph, and I've got them all together, so small versus medium versus heavy. Note here for the small damping that it has the highest peak, and that's because only a very small amount of energy is being removed from the system. And because only a small amount is removed, the amplitude is still going to be pretty great for small damping. The heavier the damping, the smaller the amplitude is going to be. And again, the faster it will return to its to its equilibrium position. This is just a brief real-world example, or what can happen if something's vibrating at its natural frequency. So back in 1940, there was a bridge in Washington, and the winds got really heavy on a particular day. And when they got really heavy, the bridge started oscillating. Well, they made it to the perfect speed, and that bridge found its resonant frequency, or that natural frequency. The wind caused it to start oscillating at that frequency. Because that is where it's going to be, I guess, most powerful, for lack of a better word there, the support cables actually broke, which decreased the amount of damping, and the bridge just began oscillating out of control until it eventually failed. So we definitely use this in the real world. Okay, let's work a quick problem. So if a car has a suspension system with a force constant of 5 times 10 to the fourth newtons per meter, how much energy must the car's shocks remove to dampen an oscillation? Okay, so it says how much energy must the car's shocks remove. So if we are removing the energy, it means it's got to be stored somewhere. So we're going to be calculating the potential energy, and that is equal to 1/2 kx squared. Well, we have the force constant and we have the displacement, so let's just plug this information in. 5 times 10 to the fourth, and this is newtons per meter, and then the displacement, and we can solve for the potential energy. It is going to be, approximately 141 joules. And that's it. Pretty simple. Okay. Now we have waves. And though when I say waves, you likely imagine an ocean wave, a wave is really just a disturbance that propagates. I'm going to write this word down, propagates. And if I ever say the wave is propagating, or you read a wave propagates at, it just means it is moving or it moves at. So it's a synonym of the word move. You've likely learned this in some other class, but as a quick refresher, the top part of a wave is called the crest. The bottom part is called the trough. The distance from one crest to another is what we call the wavelength. And the distance from the top part of a wave to the middle would be known as its amplitude. Okay. Now, as the wave is traveling, it is actually just the disturbance that's traveling. The water molecules themselves are not moving along this path. And that's why we would see a duck sort of sitting in place if a wave is traveling underneath it. It's because the disturbance, that energy, is traveling, not the actual molecules. A couple of equations you will want to know. The velocity of a wave, so the movement of a wave, is related to its wavelength divided by its period, or we can also say the velocity is equal to the frequency times the wavelength. We know that velocity is distance over time, so we can figure out the distance of a wave by looking at the velocity multiplied by how long it takes to get there. So here's a couple of equations that we might end up using. There are 2 different types of waves that we generally talk about, and those are transverse and longitudinal. But this type is transverse, and in a transverse wave, the wave is propagating horizontally, or wave is moving horizontally while the disturbance is vertical, or vice versa. So you just need to know that in a transverse wave, the disturbance, so if the disturbance is moving vertically, then the wave is going to be moving perpendicular to that. So we see perpendicular motion. We're moving this way, and then that the wave is going to be traveling horizontally in this direction. On the other hand, we have a longitudinal wave, and here the wave moves horizontally and the disturbance is also horizontal. So this person is shaking or is disturbing the spring in this manner, side to side, and the wave is traveling side to side as well, vertically. The waves from a guitar string, so the waves put out by a guitar string, are actually transverse, and we can prove this by putting a sheet of paper in front of a speaker when we play a guitar, and you would see that the disturbance and the actual wave motion are going to be perpendicular to one another, not parallel. Okay. let's work another problem. So what is the wavelength of the waves you would create in a swimming pool if you splash your hand at a rate of 2 hertz and the waves propagate or move at 0.8 meters per second? All right, this isn't so bad. So we want to know the wavelength, and we know wavelength from the other slide is velocity divided by frequency. Okay, do we have this information? Or I believe you had velocity equals frequency times wavelength, but when you rearrange that, it would look like this. Okay, so the velocity is 0.800 meters per second, and the frequency is 2 hertz. So this one's pretty straightforward. We're just going to divide and find that that wavelength would be about 0.400 meters. Okay, not terrible. Now, most waves that we see are not actually transverse or longitudinal, but they are some combination of the two. And when two waves arrive at the same point or they interfere with each other in some way, we call that superposition of a wave. So they're coming together and they're affecting each other in one of two ways. They can be constructively interfering with one another, which means they are literally building one another up. So we see here that these waves are identical. The amplitude is the same at the same point. When that happens, these waves will simply add together. They will be constructive, and the amplitude would just double. Okay. On the other hand, we have a destructive interference pattern where we see two waves and they are exactly opposite. So here we have a maximum amplitude here that is in the negative x direction. Up here, when it's negative x, it's positive x here. If we see that, the resultant wave is literally going to be non-existent and will have no amplitude. So it will be there, but it will have no amplitude. Okay. But just like most waves are a combination of transverse and longitudinal waves or motion, most waves that we see are not purely constructive or destructive, but are in fact a combination of the two. So the resultant wave does not have a nice flat part or simply doubles, but moves about sometimes in predictable patterns and sometimes not. So this is far more the most common, to have a combination of the two. Here we have something that we call a standing wave, and the name says it all. It looks like it's standing still. This happens when we have two identical waves. So these waves are identical, but they're traveling in opposite directions. So one is moving left while the other is moving right. They cause constructive interference, or if they're exactly opposite to one another, they would cause destructive interference. But either way, the wave appears to not be moving after they've combined together. So we call that a standing wave. Now, we don't always create waves with only one end of the string or spring attached to something. Sometimes we have attachments at both ends. And the points where they are attached are called nodes, and that's just where the string or wire attaches. At this point, the wave disturbance is going to be 0. Okay, and then at the antinode, we have the opposite of that. This is going to be the location of the maximum amplitude. So when something is vibrating at a fundamental frequency, that's going to be the lowest frequency. And we've seen these in a different way. So the lowest frequency. And the lowest frequency is equivalent to the longest wavelength. So the longer the wavelength, the lower the frequency. Okay, and then here's two more equations. The frequency is equal to the velocity divided by 2 times the length, or wavelength is 2 times the length. This is the same thing. I'm just noting the difference here. If it says first overtone, that's actually 2 loops. It does not mean you have 1. And if it says second overtone, that would be 3 of these loops. If it said third, you would have 4, and so on. And we could adjust our equations accordingly. So note that the more you add in one section, the smaller the wavelength is getting, so the more frequent we see those nodes occurring. Beats, and I know you've heard this term before, beats are produced by the superposition of 2 waves that have slightly different frequencies, but their amplitudes are identical. And when those waves combine, our resultant wave has some destructive interference going on, some constructive interference going on, but it occurs at regular intervals, so we can predict what the beat will be. And this has obviously been applied in music, but it's also applied in other instances as well, like in engineering and it has medical applications. Earthquakes are probably one of the best examples we have of waves and how unpredictable they can be or how they interfere. We know that sometimes you have a building that is completely demolished and the one right next to it hasn't been touched. And it could just be that the way that the earthquake's waves are interfering with one another are causing either constructive or destructive interference. But the Richter scale that we use to measure earthquakes, it actually uses both the amplitude of those waves and the energy they carry to calculate that. So the amount of energy they carry would be known as the intensity. And the intensity is equal to the power per unit area, which would be I equals P over A. And the unit for that is watts per meter squared. We're going to work a quick problem with intensity. So we have ultrasound with this intensity is being produced by a rectangular head of a medical imaging device, which measures 3 by 5. So what is its power output? Well, we know I equals P over A. We don't have the area, but we have this information. So length times width equals area. And that would be 3 times 5, which would be 15.0. And that's centimeters squared. So let's rearrange this to find power, which would be I times A. So 1.50 times 10 to the 2 watts per meter squared multiplied by 15.0 centimeters squared. And the power would be equal to approximately 0.225 watts. Not bad. So none of this math was that bad. And finally, I just want to mention this. If you've ever been at an event or a party where there was a speaker system set up, you might have noticed that depending on where you're standing, the speaker sounds quieter or it sounds louder, even though you haven't really moved that far. And this is simply because of the constructive and destructive nature of waves when they interfere with one another. So if they are interfering destructively, you might be standing at a point where the waves or where the sound is much quieter, or you can't hear it at all. It's likely just quieter. At other times, you might hear it louder, and that's because the waves are interfering and causing an amplification of the sounds, and it sounds louder to you. So that's it for the oscillatory motion and waves. In the next video, we'll learn a little bit more about sound, but this is it for now. So let me know if you have any questions, and I'll be back with the next video soon.